So, students, uh, today morning we have discussed regarding the things with respect to work without clearance volume, work with clearance volume. Then we have discussed one term with respect to clearance ratio, volumetric efficiency. Now we will be discussing some of the problems. One problem, okay, on compressor. Is my voice audible to you all clearly? Am I audible to you all clearly? Is my screen visible to you all clearly? Students, am I audible to you all clearly? Let me know. Hello? Hello? Screen is visible?
Yes, sir.
Okay. So, today morning we have discussed volumetric efficiency, effect of volume, clearance ratio, effect of volumetric efficiency. There are some two or three definitions which are asked many times in the examination. Each definition carries 2 marks. You have to write the definition and one equation. Okay. The first definition which you are seeing on the screen right now, it is known as adiabatic efficiency. It is known as adiabatic efficiency. I hope it is visible to you. Adiabatic efficiency, is it visible? Adiabatic efficiency is visible to you? Hello? So generally, what do you mean by adiabatic process, students? What do you mean by adiabatic process? What do you mean by adiabatic process? For adiabatic process, what is the heat transfer, students? For adiabatic process, what is the heat transfer, students? Do you understand my question? For adiabatic process, what is the heat transfer? What is the value of Q? Hello?
Zero, sir.
Zero, right? So adiabatic efficiency is with respect to that adiabatic process itself. So here what it says, see, the ratio of isentropic work input to the actual work input. So adiabatic process is also known as reversible isentropic process. Already I have told in the vapor power cycle chapter for you. So whatever isentropic work input is there, it is a theoretical isentropic work input. But actually, when you go practically, you don't achieve the adiabatic process or the isentropic process. So you need to check how much it is been differing the ratio from isentropic to actual. We call that term as adiabatic efficiency. Okay. Then a similar next definition we have students, isothermal efficiency. So for isothermal efficiency, which parameter remains constant out of pressure, volume, temperature? For isothermal efficiency, which parameter remains constant, students, out of pressure, volume, temperature? Students, from pressure, volume, and temperature, which parameter is constant for isothermal process? Temperature, isothermal temperature remains constant. So therefore, here isothermal work input to the actual work input is a thing, but it is representing the isothermal efficiency. See, the definitions are very simple. Isothermal work input, no, if you compare the actual work input during the compression process, it is isothermal efficiency. Similarly, adiabatic work input with the actual work input during the compression process, it is adiabatic efficiency. Then mechanical efficiency, ನಿಮ್ಗೆ ಗೊತ್ತೈತಿ from first semester you are learning IP by BP. It is mechanical efficiency. I hope this point is clear to you. Now, one problem,
Excuse
students.
me, sir.
Yes, yes, yes.
Vishnu wants the join to meeting.
Vishnu wants to join. Okay, 1 minute. I will check it. Vishnu, have you joined? Vishnu, have you joined? I have given permission now. Vishnu, reply me. I think he has joined. I think Vishnu, have you joined? Vishnu, Vishnu, have you joined? I think he has joined. Or check him. Vishnu, have you joined?
No, sir, he is not there.
Hello. Students, is my screen visible to you?
Yes, sir.
Not visible. Is not there. Okay. Check. Is my screen visible to you clearly now?
Visible, sir.
I think he has joined now. Okay. So the problem which we'll be discussing now is a simple problem, students. It is a basic problem. So observe the things what they have given the question. Here it is said that, please observe here from the first word itself. A single stage. A single stage acting air compressor, 30 centimeter bore, 40 centimeter stroke is running at a speed of 100 rpm. It takes in air at 1 bar and 20 degrees Celsius, compresses into a pressure of 5 bar. Find the power required to drive when the compression is first one isothermal, second one P into V to the power of 1.2 is equal to C, third one adiabatic. Also find the isothermal efficiencies for the cases 2 and 3. Neglect the clearance volume. Okay. First, note down the given things. Remember, students, always a single stage means the n value is equal to 1. If it is double stage, n is equal to 2. Bore, symbol you know, d it is 0.3 30 centimeter means 3 meters, 0.3 meters. Stroke, 0.4 meter. Then capital N, speed 100 rpm. Then pressure inlet P1 is equal to 1 bar. 1 bar is equal to how much kilopascal, students? 1 bar is equal to how much kilopascal? What I am asking, 1 bar is equal to how much kilopascal? Or how much pascal? Students, are you listening what I am saying? 1 bar is equal to how much pascal or kilopascal? Hello? 1 bar is equal to how much pascal or kilopascal? You have to remember these things, they are very important. 1 bar is equal to 100 kilopascal. Then temperature T1, it is 20 degrees Celsius. Add 273 for this one. You get it in kelvins, it is 293 kelvins. Remember, students, always temperature for this particular module should be in kelvins itself. Please take care. Then pressure P2, how much it is? 5 bar. 5 bar means how much kilopascal? It is 500 kilopascal. Students, what I am saying? 5 bar is equal to 500 kilopascal. Am I audible to you all clearly? Hello? Are you listening what I am saying? Hello students? Then what you should find out? Power required. See students, work done with respect to time is what, students? Can you tell me work with respect to time is what? Hello students. Work done with respect to time is known as work done with respect to time is known as. Are you listening what I am saying? The rate of doing work is what? The rate of doing work is what? It is power P. It is power P. Okay. So now you need to find out the power required for what process? Compression. P into e to the power of 1.2 is equal to C, which means it is an process, polytropic process, adiabatic process. You need to find this one. So if you plot a graph, there is no clearance volume in this particular problem. So when you plot a graph, how it looks, please observe your first everybody on the screen. This is your pressure volume diagram. Generally, a compressor without clearance volume, how it looks like this, students. Like this it is. Suction, compression, delivery. This curve is what, students? It is polytropic curve. P into V to the power of 1.2 is equal to C. This curve it is. Now he has asked isothermal. For isothermal, what is the equation, students? It is P into V is equal to C. Okay. So I can write this curve now. I'll write this curve in this fashion now. Isothermal. See. This red color is isothermal process. That is P into V is equal to C. P into V is equal to C. Then students, final we have what? Adiabatic process. Adiabatic means gamma value is 1.4. So if it is 1.4, the curve like this it is. This is P into V to the power of 1.4 is equal to C, because gamma value for air is 1.4. For all these, you have to find out the power required as well as the isothermal efficiencies for case 2 and 3 also. Am I audible to all clearly, students?
Yes, sir.
Okay. Nobody replied me whether the network is there or not. I forgot. Hence I asked you. I think we shall again go with the problem now. Yes. These are the given data. As I said, one more important point, students. One more important point I would like to tell you here is for a single stage here. For a single stage, the notification what to take is take it as X. Single stage means X is equal to 1, double stage means X is equal to 2. Why I said this one is because this one 1.2 we have taken the symbol as small n. So don't get confused. You can take single stage, double stage symbol as X. So I have written the given data here: speed 100 rpm, bore 0.3 meter, stroke 0.4 meter, pressure 1 bar, temperature 20 degrees Celsius, P2 5 bar, yeah. Then Polytropic process N is equal to 1.2. R value for air it is 0.287. You need to remember this one. And this is the graph which I was discussing with you. Okay. So as I was saying, once again I will show you here. This is isothermal process. You can see here. PV is equal to C. They have written. Then next, this is a polytropic process. PV into N to the power is equal to C. You can see they have highlighted here. Then last comes adiabatic PV raised to gamma is equal to C. This one. Okay. Now, first we'll find out the swept volume. Swept volume is equal to pi by 4 d square L. So here, if you observe from the PV diagram students carefully, if you observe this pressure volume diagram from here to here, okay, this is process 1 starts, and this is different positions 2, 2 dash, 2 double dash. We are having different positions here, okay. So this is position number 1. So from origin to one, there is only swept volume Vs. So what you can say, Vs is equal to V1 according to this particular graph. So therefore, I can write as there is no clearance volume here, V1 is equal to Vs, and it is in meter cube per cycle students. What I will do is, I will take this with respect to what? The RPM. So RPM is, we have said 100 RPM, so I will multiply 100 RPM divided by 60, that is in a meter cube per second, you are going to get 0.047 meter cube per second. That is V1. Now, your gas equation. P1 V1 is equal to MRT1. You will write the value of, get the value of M. As I said, students, carefully. Pressure value in kilopascal, you can see here. Then this is the value of temperature in Kelvin. 20 plus 273. We get the value of mass in kg. How much? 0.055 kg per second. It is mass for it. Then for isothermal process, you know your work expression which you have studied in our BTD subject. P1 V1 ln of V2 by V1. But instead of that, we are having P2 and P1. What I will do is, I will reverse this equation as P1 V1 ln of V2 by P1. So all terms are there. I will substitute and I'll get the value of directly power itself, kilowatt. Why I am getting in terms of kilowatt is, just now we have found out the value of V1 students. It is in terms of what? Meter cube per second. So therefore, the resulting answer what you get in terms of kilowatt itself. That is the reason I substituted there the speed. Similarly, next, polytropic. So for polytropic, you need to find out the temperature pressure relation that we have used here, students. T2 by T1 is equal to P2 by P1 raised to N minus 1 by N, where you can find out the value of temperature T2, which means your gas equation, your polytropic work process for a compressor. This is your equation, P into N by N minus 1 MR into T2 minus T1 without clearance volume. I substitute the value, I get it as what? How much? 8.54 kilowatts. This is for work input for a compressor without clearance volume. So you have learned without clearance volume. This is the equation, students. You are getting in this form also. And finally, for the isothermal efficiency, we have isothermal power by actual power. You get it as 80 to 88.52% if you substitute. Similarly, for adiabatic process, we use the gas relation, that is the pressure temperature relation. You get the value of T2, substitute in the work transfer equation, gamma by gamma minus 1 MR into T2 minus T1. On substitution, you get the value of P as what? 9.45 kilowatt. Your equations we have studied for the work input. So here also isothermal efficiency, isothermal by actual power. So isothermal power is, we have got 7.56 Actual power for isothermal for this process, we take it from here. So that is 9.45 kilowatt. We substitute and get the answer as 80%. Okay. So this is the discussion of this simple problem. Okay. Now, one small concept we'll discuss and we shall stop here only. One concept we call it as free air delivered. We call this concept as what? We call it as free air delivered, students. What is this free air delivered? When the air is being compressed, that volume of air, okay, that volume of air with respect to the corresponding atmospheric conditions, whatever it is there, we call it as free air delivered. So, using a small relation we have established saying that free air delivered conditions, that is pressure, volume, and temperature, given as a suffix F, that is pressure, volume, temperature, the free air delivered with respect to the pressure, volume, and temperature of with the clearance volume, that is V1 minus V4. We can write volume of air free delivered Vf is equal to, these two terms come to the other side, we write it as like this. So therefore, the overall efficiency, it is Vf by V1 minus Vc, where the value of Vf, just now we have discussed, students. Just now we have discussed Vf is what? P1 into Tf divided by Pf into T1 into V1 minus V4. This equation we substitute here. We substitute the value of Vf. That is, this is the value of Vf, students. This is the value of Vf. So on substitution, and after I take this form, that is this form V1 minus V4 by V1 minus Vc, it is nothing but it is representing the volumetric equation which we discussed in the morning's class. So this term V1 minus V4 by V1 minus V3, I write it in this form like this: 1 plus C minus C Q2 by P1 raised to the power of 1 by N. I hope this point is clear to you. Is it clear, students? Hello? Is it clear to you? If you have any doubts, you can ask, students. Hello?
No, sir.
Okay then. So what we will do is stop today here only. And in the next class, it is on Monday, we will be discussing again next method of compression process. Okay? We shall stop here, students. Thank you.
Sir,
Yes.
sir,
Yes,
we
yes.
needed the notes of second model which was taught by Alu sir, and we got
Second module, that is, I think it's IC engine.
IC
Gas
engine, gas power cycles, and vapor power cycles.
Okay, okay. I will communicate with sir and I will send you the notes in the Google Classroom. Okay?
Okay, sir. Thank you.
Okay, okay. I will send
Excuse
it.
me, sir.
Yes, yes, yes.
Sir, can we get this recorded video in classroom, sir?
Record video. Okay, I will send. I will send the Google Classroom. I will send it today.
Okay, thank you, sir.
Okay.
Sir.